Hey. Okay, now they're up. Yeah. Sorry, could you say that louder? Yeah, so they were supposed to be done this weekend, but they were not. So, will we get them out to you today? It depends on who responds to my messages on Slack. So, yeah, I apologize for that. So, right, let's catch up for the cameras. Uno, midterm grades, just what we were just saying. Yes, they're on their way. I'm sorry, they were supposed to already be out. This weekend, not this weekend, this week, Wednesday, in fact, May 17th, your project proposals are due. To turn in your project proposals, you already have a GitHub repo. There's already that, template in there. Fill up the template. Make sure that you commit and push those changes. When those changes are in your repo, that's where your TA will be grading. Whatever's in your repo on GitHub. So make sure you push. Okay? You're going to get feedback, just like in COGS 108. For those of you that have been in COGS 108, you're going to get feedback on the issues of that repo. Within a week, hopefully more like within 4 days, your TA is going to have read your proposal, will give you feedback through GitHub issues. Okay? If you haven't used GitHub issues, there's threads in there. Just to show you, like, let's go 118, lectures. When did I last do this class? Was it fall 22? Was it winter? Can't even remember. Okay, winter 23. Right, here's a random. I just totally picked it at random. I have no idea if it's any good, right? Here's the kind of feedback that somebody got. Right? It gives you points, which of course students only care about points, except for these kinds of things in here, which really tell us that, oh, we need some sort of benchmark model, right? So these bits of feedback, if you address them, you're going to get the points that are missing back, right? If on the checkpoint you fixed this problem where it says you need a benchmark model, then on the checkpoint you'll get these missing points from that lack of benchmark model back. Okay? And if something isn't clear, this is a threaded conversation in here. All right? You can say, hey, what do you mean by blah, 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 and your TA will answer. So please do use GitHub issues interactivity when you need it. If you want to clarify if this is sufficient to address your concern, that's a good place. All right? So please remember, push your changes to your repo or else they're not there for grading. Anybody else got any other questions? Project proposal seems like it's in hand. Who hasn't started on their project proposal and wants to be brave and raise their hand? Yeah, thank you, brave people. I know it's real, okay? I know that a lot of you last minute it. Okay, if you have concerns or questions, please get us through Campus Wire or in office hours, all right? Okay, let's go back to today is fun. Ensembles are some of my favorite things in machine learning. So with ensembles, the idea is pretty easy. It's wisdom of the crowds. Anybody ever done like a fun fair thing where you have a big jar of marbles and you've got to guess how many marbles, or like proper 4-H fair, like here's a prize hog, guess how much the hog weighs? And there's a couple of nods. Nobody grew up super rural like me and went to 4-H fairs. Okay. Well, the idea of those things is when you look at every person guessing how many marbles or how heavy that hog is, every person is wrong, okay? Wrong in different amounts. Some people may actually be great guessers, and they may be pretty close. But the thing is, as long as every single person making a guess is making their own independent guess without being influenced by other people, right? So no situations where you have a bunch of people standing around yelling, 1,800 pounds! That's how heavy that hog is. Because as soon as a person hears another person say 1,800 pounds, that's a psychological anchor. And there's no way that that person's going to guess 600 pounds. Like, it's just not going to be conceivable. Like, all of your answers from that point, as soon as you hear somebody else's answer, are going to be anchored by that other answer. So it's a little bit of psych for you free, right? It's perceptual anchoring. It's a real thing. So the key to getting an ensemble that is better than individuals is having each member of the ensemble making decisions independently. All the votes have to be silent without other people being able to hear them. As long as you do that, that mean old racist, Francis Galton, who is the father of modern statistics, right? Francis Galton, back in 1800 whatever, figured out that the mean of all the people guessing how heavy the hog is better than any individual guess. Why is the mean better? Well, it's because everybody makes a different kind of error, and every error is independent. And if you average across errors, that's what we do in statistics, right? We average across errors to find the truth. And as long as every individual in the ensemble is at least slightly better than chance level, then you can average across all those errors and get arbitrarily good. As long as you got enough votes, as long as those votes are independent. So that is what ensemble learning is about. We're going to get through it here today, particularly to look at random forests if I'm fast enough. But along the ways, we're going to discover all the principles that are used in ensemble learning in general. Okay? So our target of getting as far as random forests, you may have already guessed from their name, they are forests of trees. And we've already seen decision trees, right? We know decision trees. They're awesome. They're super fast at test time, so that's pretty useful. They're not terrible at training time. They've got all kinds of cool properties, like the fact that they're interpretable, which makes them slightly unusual in machine learning land. We also know what they're shit at, which is overfitting. So the thing about an ensemble of trees is that because all we need is for each individual member of the ensemble to be slightly better than chance, and we can make an ensemble that's really great. Okay? So that overfitting problem is not so much of a problem, and we can get all the other advantages. Okay. So, two separate ensembles we're going to talk about today, bagging trees and random forests. They're highly related. So what is a bagging tree? What are ensemble methods? So before we talk about ensembles, we maybe have to have a word about voting. You will often see things like people talking about a majority vote when they actually mean something different. I'm gonna throw this out there for the pedants, right? A unanimous vote, I think everybody understands. Majority vote gets misused all the time. Majority literally means that you do have to have more than 50%. Okay? Frequently in politics, like presidential elections, we don't come to majority. It's like 46% versus 45%, right? And everybody in the middle is voting for a third party or doing something else. So just to be clear, a majority vote is actually something where you're supposed to get past the halfway mark. And other political systems other than ours know this a little bit better, and they talk about plurality, which is actually just, hey, this is where the most votes lie. It's not over 50%, but this is not the vast majority. That's exactly what it is not. It is not the majority. It is the largest number. This plurality is also statistically the mode. Right? Yeah.
Would you say that the circles there, if that was a vote, would be winning by plurality vote?
So, sorry, all of these lines the circles would win, right? By plurality, majority, or unanimity.
Sorry, I meant for the bottom one.
For the bottom one, this is a plurality, yes. Yeah, that is a plurality. Okay, I'm saying that for the pedants in the room. Okay? Now, when typically you see ensembles, they will usually say majority vote. That is, I would call that the baseline version of an ensemble of machine learning algorithms. But half the time when an author says majority vote, what they actually mean is the mode of votes. And that is, of course, not actually majority, but a plurality. So just an FYI, because I'm not the only person you will ever read their slides or lecture notes on, you will regularly see people use majority in ensembles when what they mean is plurality, when what they mean is the mode, the most frequent vote among the ensemble. Okay? That's why I took the time to distinguish there. Okay, what is an ensemble? An ensemble is a setup where we have a set of machine learning algorithms. Each one of them is fully trained. And we give each machine learning algorithm the same data point. Each machine learning algorithm makes its own vote about whether that's positive class or a negative class. And then we take the vote. We take the mode, and we say, okay, the most common answer here is 1, so it's positive class. That's what my individual data point is labeled as. Make sense? Yeah?
How do we determine what the algorithms are?
Well, that is a topic, right? So when we get there, we can find out that we can put anything we want, really, in those slots. Okay, to answer your question. Decision trees are simply really easy because they're relatively computationally simple. And the key to what we really need out of an ensemble is just that each learner is better than chance. Doesn't matter if it's 1% better than chance. As long as it's better than chance, we can create a system that is arbitrarily good. Okay? So since we don't need a really powerful system, we can put really weak, fast-to-learn learners in each slot. Now, if you want to put something crazy in each one of those slots, feel free. But you don't need it. Right, so in the pre-video, I covered this in greater depth. I'm just going to kind of flash over it now. if you want to convince yourself why you just need just a little better than chance, it turns out that it's essentially the binomial PDF. When you look at a situation where you have, say, 11 learners in the ensemble, and you want to get a situation, you want to calculate how likely is this whole ensemble to give me the correct answer. Okay? Well, it's pretty simple. It turns out for the ensemble to give me the correct answer, I need to have, for 11 learners, I need to have more than half, right? That would be 6. 6 of them have to say the right answer. How likely am I to get 6 learners out of 11 wrong? That's what I'm asking the question. All 6 of these learners have to be wrong at the same time for me to be wrong as an ensemble, right? So that's what this formula is in here. What's the probability of 6 out of 11 being wrong? Okay? Again, if you want to know more, go through the pre-video where I cover this slower and in greater detail. But that binomial theorem, you can take a base error rate, just assuming that every learner on the ensemble is got the same likelihood of making an error. Okay? So that's what this E is, the likelihood of making an error, the base error rate, right? And if that E, oh my goodness, I cannot draw today. If that E is less than 0.5 for a binary decision, then we are better than chance, right? Doesn't matter how much smaller than 0.5, just a little bit smaller. That's all we need. So if I plot the base error rate here, obviously that's the diagonal because this is 0 base error, this is 0.2 base error, right? This is 0.6 base error, so obviously the base error rate is going to be this diagonal. And I plot the error rate of the entire ensemble, this summation over the binomial PDF. Then I'm going to get this line. Okay? So as long as I start off less than 0.5, right, anywhere to the left of this point right here, the blue line is underneath the orange line. The ensemble is better than the base classifier by itself, right? Now, here's the mind-blowing trick. This S-shaped curve, well, that's for a given number of classifiers in the ensemble. If I have fewer classifiers on the ensemble, then that curve is more shallow. And if I have more classifiers on the ensemble, then that curve is more steep. All I've got to do to get arbitrarily low error rates is just add more and more classifiers. I can't draw today at all, sorry. Let's just add more and more classifiers until I have this. And I can get arbitrarily good error rates with something that's just barely better than chance, 0.499999999. Pretty crazy, huh? So that's why ensembles are awesome. Okay. So one other thing I want to throw out there is the idea of soft voting. Soft voting just means instead of counting up votes, if our classifiers are quote-unquote well-calibrated, that means they output probabilities of classification that are proper probabilities. Like, for instance, logistic regression, right? Logistic regression tells you what's the probability of positive class. So as long as you've got a probability output on a classifier, what you can do is, instead of counting votes, you can sum up the probabilities. You can do it in a weighted fashion, like you show here, where maybe some classifiers count more than others. But even if this weighting function is just ones, what you're doing is you're just summing up the probabilities, okay? Taking the average over the probabilities. Okay, so in that kind of a situation, what you've got is something like this, right? Where each classifier is voting for its belief on the probability of a given data point being positive class. And this is the weighted sum of all those votes. Any questions? Yeah?
How do you determine whether or not to make all classifiers equal?
It depends on the algorithm we're talking about. I'm setting up some fairly general tools, and then different algorithms will do different things with this, okay? So various versions of ensembles have explicit ways of setting the weights during the training process. An example of that is boosting. Okay, we'll talk about boosting hopefully on Wednesday.
On the previous two slides before this one, we went over the binomial distribution.
Yeah.
Why did we do the summation from k to n instead of
Yeah.
multiplying something independent?
So getting 6 wrong answers at the same time out of the ensemble, that's the case where exactly. So you need to also check for 7 wrong and 8 wrong and 9 wrong and 10 wrong and 11 wrong. And that's where the sum is. Yep. Mm-hmm.
How are you like making sure that the errors for each algorithm are the same?
Great question. So for this math to work requires independence of errors, statistical independence, right? Every algorithm has to make its mistakes differently, and no correlations on like this data point's just hard and they all get it wrong, right? So you're absolutely correct. How do you ensure that? Generically, we basically don't, right? Theoretically, by having everybody train separately and having each algorithm get something that causes it to do things a little differently. So that can be, for instance, different subsets of training data for different algorithms. They trained on different data, therefore they make different weights, therefore they do test differently, right? Some algorithms have random variables in them, randomness. Random initialization is another method we use to help ensure that. This is a good question. Yeah. Good? Okay. So, all right. Now I'm going to add in one other tool. We've already talked about the bootstrap sampling, sampling with replacement. If you're interested in the etymology of bootstrap, you can feel free to read this on your own time, but I'm going to boogie for time. Right? Sampling with replacement means that when you take the original data set and you take a resampling of it, you can get one data point, like this orange data point in there, multiple times, right? We talked about this previously. In fact, in the bootstrap sampling, in the limit, as we go up to the replacing, if it's an n-long data set, and we sample n times with replacement, then as that n gets very, very big, the probability of a data point not being chosen at all goes towards 36%-ish. So it's a pretty high probability that one piece of data will never make it into the bootstrap sample, right? And that means the inverse is true, right? The probability that a data point will be chosen as we get to a large number of samples is around 63%-ish. Okay? So now we go back to your question. how do we create difference among the different classifiers? Well, bootstrap aggregation, also known as bagging, is our first method of building an ensemble. What we do is we train each classifier on a different bootstrap sample of the same data set. Because each classifier has got a different training set now, each classifier is probably going to make a different set of mistakes. Okay? So bagging or bootstrap aggregation looks like this. What we do is we have our entire training data set. If we're going to have 3 classifiers in our ensemble, then we make 3 bootstrap resamples, the same size. Actually, this is a bad drawing now that I look at it. Generically speaking, these are going to be the same size as the original training set. That's what my notation there means. The absolute value signs are like the size of the training set, right? So even though they're each the same in the size of the training set, because of bootstrap replacement, they've got different components in them. They make different answers because of that. Super simple, right? Now, you can put anything you want into that bagging system. You can put any kind of classifier. Whatever your base classifier is, it doesn't matter. We're going to make another bootstrap sample for however many of these we got. And then at the end of the day, what we're going to do is we're going to take the mode vote of those classifiers. H is a notation that you'll see a lot for different classifiers. Think of H like a hypothesis. Each classifier in the ensemble generates a hypothesis of what the right answer should be. We're going to take all these hypotheses, and we're going to take the most common one of them and use it as the output of the bagger. Okay? So you can put anything you want in those hypotheses. You can put a support vector machine, you can put a nearest neighbor algorithm, you can put a decision tree. Again, generically speaking, we just need this to be okay. Each classifier just needs to be okay at its job. So you don't have to put a lot of effort. You don't have to put in something really computationally expensive. Everybody tracking? Got any questions at this point? Okay. So, remember that 36% we left out of every sample? We've got a built-in tester validation set now. Okay, here's a small subtlety to think about. For classifier 1, we left out samples 9, 14, and 17, right? 9, 14, and 17 are not in classifier 1. Okay? Classifier 2 left out samples 9, 12, and 23. Okay. When we want to see test set performance, 2 of those classifiers both left out sample 9. So for sample 9, we can take the test set error of classifiers 1 and 2, the 2 classifiers that didn't have it in the bootstrap sample, right? We got to use only those classifiers that never saw sample 9. Okay? That gives us what's called the out-of-bag error. If it wasn't in that classifier's bag during the bootstrap aggregation, we can use it for a test sample for that classifier. And we can do that for every data sample. We can take all those classifiers that left it out of their bag and check those classifiers' performance on that data sample. Sound good? You do that over all the data samples, and now you can get the average error across that out of bag. Again, each classifier has a different set of out of bag. Okay? So you've only tested each classifier on the things it didn't train on. Now, if you look at this graph, you'll see that out of bag error is definitively above the test set error in blue. Okay? Out of bag error is harsher, right? It's more pessimistic. The error is higher. It is a biased statistic, just to bring it back to bias variance trade-off. Out of bag error is biased because it only uses a small set of the data, right? Only 36% of the data. That's why it's pessimistic. Okay, turns out you can make, because anything that's biased systematically, if you know the nature of the bias, you can try to undo the bias. Okay, so we can make a correction. This is called the 0.632 estimate, right? Because most of the data is over here in the training set accuracy, but we know we're going to do better on the training set because we're overfit to it, we can make a systematic correction and take part of our training error and combine it with part of our out-of-bag error. This 0.632 estimate corrects for the pessimistic bias of the out-of-bag error. So this 632, and even more this 0.632 plus algorithm, which is an even more sophisticated correction of the systematic bias. These are ways in which people can use the out-of-bag estimate to get to getting a test set or a validation set understanding, depending on what you're trying to do, of the performance of their ensemble. As long as your ensemble is a bagging ensemble, which is created using bootstraps, right? Because this is predicated on a bootstrap. People are looking a little bit more blank on this one than the last two slides. I don't want you to focus on the details of this math, of the 632 plus. The 632 plus, it's complicated. There's a lot there. I don't really understand the derivation of the 0.632 plus, okay? It's just something that, like, there's a recipe, you follow it, okay? To be brutally honest, scikit-learn doesn't implement either of these, which is kind of weird in my opinion, because why not correct for this bias? But roughly speaking, if you know that you're out of bag, if you just want to use out of bag error, and you just understand that it's a pessimistic estimate, it's probably good enough for most cases, right? You just know it's actually going to be better than you're calculating. What if you're doing model selection? What if you're trying to decide between using, you're using k nearest neighbors bags, and you've got k, how many neighbors you're using? And you want to choose between k equals 3, k equals 5, k equals 7, k equals 9, and you're using out-of-bag error. Do you care about this bias? Using out-of-bag error as model selection to pick k, trying different k values for your ensemble. Yeah?
Yes.
Why is that?
I don't know.
It was just a random response. All right, great. So, let me give you a hint. The answer is no. And the question is why? every estimate is pessimistic in the same way. You're only comparing k equals 3 versus k equals 5 versus k equals 7. They're all pessimistically biased. So who cares, right? They're all systematically wrong in the same direction, so you can still make the comparison with this. It's like having a meter stick that's like 3 inches too short. Well, why did I mix meters and inches? Because I'm not English or French, but American, right? So the idea is that the same yardstick's being applied. Even if it's a bad yardstick objectively, it's the same yardstick, okay? So this is why scikit-learn never bothers with 0.632 or any of these other correction factors. But if you wanted to say, how good will my ensemble be next year when a new batch of data comes in, then you probably want to correct, because you know this is going to be pessimistic. And if you want to say how good we're going to be next year, correct. If you're just doing model selection, if you're doing validation, who cares? Make most sense? Yeah.
So just to kind of generalize a little bit, if you would care more about eliminating your bias when you're looking for more kind of, to put it simply, more of like a generalized long-term, something that would have more weight than immediately selecting, like, oh, I want which model works best, which algorithm works best, or whatever.
Yeah.
Because it's all biased in the same direction, but if you're just using that one bias term that's very pessimistic and you want like a high value, but you have no idea how high it is from there.
Yeah.
Probably the answer to it.
It is true that you, without a correction, without a bit of math telling you how to correct, you don't know how biased it is, right? But the thing about the 0.632 and the 0.632 plus is that we know, roughly, on average, over training sets, how biased it is. So that's the idea, right? And if you want to know exact values, because you need to estimate performance in a test set kind of way, correct. And if what you want to do is you want to, in a validation set kind of way, just pick among different hyperparameters, don't bother. Okay. So this is a bagging classifier. This is how we do it. We can build k-bootstrap samples for k classifiers and evaluate on the out-of-bag set, potentially, if we care, correcting for the pessimistic bias of the out-of-bag. Okay? So this is a bagging ensemble and how we use it to get either a test set estimate, in which case we will probably correct, or a validation set estimate to pick the best hyperparameter to do model selection, in which case we probably won't bother. If you're interested in actually correcting, one library I can suggest that will do it for you is there's this library called MLExtend. I'll just write it here. It comes from Sebastian Raschke, whose slides I steal regularly for this class. So you can give that a shot. It implements both these estimates. Okay. So in terms of bias variance, what are bagging ensembles doing? Well, because the bagging model is essentially taking a central estimate, it's not taking a mean, it's taking a mode, right? It's taking a mode, which is a central estimate, like mean. It's averaging, so to speak, to put it in kind of intuitive terms. We're getting rid of the variance, right? We're taking a central estimate of a variable estimate. Every single ensemble member has got its own unique errors. They're variable. We're taking a centralized version of that, and we're taking that, and that is therefore less variable, less prone to overfitting in general. Okay, I went through the bias variance decomposition in math during the pre-lecture. For those of you that actually watched it, I'm curious. Did that make any sense? No? Okay. I want to say this. I am never going to test you on a test question on like doing that derivation yourself. The reason I have that in there is because I want to convince you this thing actually exists, right? If you can see it mathematically fall out of this idea that we start from the fundamental question of machine learning, right? The fundamental question is, hey, I have this truth. Well, I think I actually have that on the slide. I do, right? We have this truth. Y. There's some number I can measure. These labels on my training set, these labels Y. There's some kind of truth. And that truth contains both a real relationship between X and Y, hidden with a little bit of noise, that epsilon, right? That epsilon is a little bit of noise. Every one of those Y data labels, sometimes they're corrupted by random noise. Okay? And I want to see the difference between that Y and my estimator. This is my machine learning prediction, F hat, right? Hat is an estimate that my machine learning system makes. What's the difference between truth and my estimator? Taken as an average over lots of training sets. That's what that E says. On average, over many possible training sets on the same problem. What is my expected average error between truth and my machine learning prediction? So the rest of this is math that I went through in detail during that pre-lecture. But the thing is you can do a bunch of frickin' algebra and you end up with this breakdown. And it turns out this breakdown is the bias squared, the systematic difference between my prediction, right? This is my prediction today, right now, on this training set, f of x0. And this is the expected value of my prediction over many training sets. So this is my bias, my systematic error, right? Okay, and likewise, this is my variance between the expected value of this minus the expected value on this particular data set squared. So this is the variance term. And so we have these three components. Irreducible error, which is fundamentally that thing right there. Can't ever get rid of it. Okay? Bias and variance. So all that math was just to convince you that even though I just keep saying this, you could demonstrate it to yourself with a little bit of algebra. Okay? The cool thing about that is because all of those things are calculatable. If you go to this little demo right here, that's a clickable link. That's part of the scikit docs. I'm too lazy. I'm not going to do this thing myself. This is just in the scikit docs. You can see the script that generates this. This is decision tree regression. Remember decision tree regression? All you do is you take your data points and you break it up into tree, and the tree, for this node, you just guess the mean value across those x's, right? So this is, in the red line here, that is one particular decision tree regressor on a sinusoid, on a true sinusoid, okay? That faint ghosts underneath it, those are a bunch of other individual decision tree regressors that are, of course, different. Here we can see the total amount of error as we go across the x-axis. Okay? This is the bias term that we can calculate because we have those expectations. You can't hardly see it, but there's a green line underneath this. That's the variance term. And the turquoise line on top is the irreducible noise. Okay, over here we have a set of bagging trees, right? An ensemble of decision trees. Okay, just looking at the regression line, you can see it's not as crazy off on average off the sinusoid. You can see that the regression line doesn't quite reach those training data points in blue. It's actually short of them, right? So it's short of those training points. That red line stops short of them. So it's regularized, right? It's not reaching all the way to that noisy training data point. And on average, the error is a little bit closer to that sinusoid. Just like if you look across the average here, it's a little bit lower than the average here. There's a little bit less error. Of note, you can really see that the variance term is quite a lot lower in the bagging tree. Okay? Again, these are just empirically calculated on this one problem using these equations right here. And if you want to see it in more detail, go look at the docs. Okay, I'm finally here. I made it to random forests. Woof. 2 minutes. Ready? Random forests in 2 minutes. I'm joking. Okay. Random forests are actually easy to do in 2 minutes because we've already talked about bagging. Random forests are bagging plus. Bagging plus, not just resampling the rows of the data points, but also the columns. An extra level of variability. Each tree, or depending upon how you do it, either each tree in the forest or each node in a tree gets a random resampling of the available features, as well as a random resampling of the available data points. So there are two different random forest methods. In random forest method 1, right? So this is that each tree gets a random subset of the features. This is the original flavor. Okay? This version, which is more popularized, every single node gets a different subset of the features. Every node in the tree. Right? Lots of extra induction of variability to force each one of these learners to make a different kind of mistake than any other learner. And that extra variability guarantees us, as we get large numbers of learners, really good results as the ensemble goes. Okay? 1 minute for questions. I will hit a little bit more about this on Wednesday, so don't worry about that. No questions, though? All right. Have fun. Hey.
I have a question about SVM.
Okay.
I was wondering I know in one of the pre-lectures you said like this part is units of B and this part is absolute units. I was just wondering why that is, and then where, like,
Yeah.
how do you go from here to there?
Okay. Remember the picture that I'll turn this off so I don't broadcast everywhere.